Hi, Addison from Addison Academy here, and welcome to AP Physics. Today I thought we'd walk through one of the free response questions on the 2025 AP because I've been doing a lot of physics and I noticed that it's pretty tough and there aren't a lot of good explanations out there for AP Physics. So I thought I'd provide one. On the left, we have the actual question from the AP. In the middle, we have our paper where we're going to do our work. And on the right-hand side, we have the answer key, which is helpful but doesn't come with any explanations. So that's what this video is all about. All right, step one. If you're familiar with my method, it's to do the Geico, or to figure out what the question is asking you. Get exactly intelligently clear on the question. The first part of this question is asking you for the electric field as a function of the radius. So we can go ahead and start our answer. It's going to look like that. It tells us to use Gauss's law. So all we've got to do next is write down Gauss's law. I'm going to replace E with E as a function of R, just because the problem has clued us in that E will be a function of R and that's what we're solving for. So there's Gauss's law. Now we have to pick a Gaussian surface. So if we come over here to this cylinder, okay, let's look at it from the cross-sectional view for a second. We're going to be between R1 and R2. So here's R1, here's R2. So a good choice for a Gaussian surface would be somewhere in between. Okay. Now it's not going to be just two-dimensional. It's also going to need to enclose this inner cylinder, and so it's going to need to be a cylinder in and of itself. Okay. Now, if we think about the charge coming out of this inner cylindrical shell, the charge would be going in this direction. Okay, going outward. And so all of it is passing through the walls of our Gaussian surface. And none of it is passing through the end caps. We don't have any charge going this way. Okay? So we can ignore the top and bottom of our Gaussian cylinder and just consider this outer sheet. Now we need to figure out what the area of that is. Well, if you take a cylinder and you sort of unroll it like that, you get a rectangle. And what's this top line going to be? Well, that used to be the circumference of the circle. So it's 2 pi r. And what's the length here of our cylinder? Well, that was given to us as L. So the area of our Gaussian cylinder is 2 pi r L. Since the electric field is constant and it's not dependent on the area of our Gaussian cylinder, we can simply pull it out of the equation. This is where some people get a little bit confused because this is a constant. So we can pull it out. It's independent of our area and just take the integral dA, which is simply equal to the area. Okay, so then we get this equation, the electric field times the area, and the area is 2 pi RL. So now we have the electric field R times 2 pi RL. Now, none of that would be helpful unless we had an equal sign. It's equal to the enclosed charge over epsilon naught. Well, what is the enclosed charge? It's equal to the surface density of that inner cylindrical shell times the area of that inner cylindrical shell over epsilon naught. What's the area of the inner cylindrical shell? Well, that would be 2 pi r1L over epsilon naught. Okay, same idea, but now we're using an R1 because it's an actual R, so it's fixed. Now, quite a bit of stuff's going to cancel out. 2 pi and L all disappear. 2 pi and L disappear. And so what's left? We have the electric field times R is equal to the density times R1 over epsilon naught. So go ahead and just divide both sides of that equation by R, and we get our answer. Okay? So the electric field there is based on 3 constants and then divided by the radius, which makes sense because as we move further away, the electric field would decrease. Okay, you can see here in the answer key, it's pretty much saying exactly what we have. If you write down Gauss's law and try something, you get some points. If you use the correct Gaussian surface, 2 pi RL here, an unrolled cylinder, the area of the walls, you get some more points. And then here we can see the actual derivation. All right, moving on to the second part of the equation. It's asking us for the absolute value of the potential difference. So absolute value potential difference. I know that potential difference equals negative the integral. In this case, it would be from, so if we look at the cross-sectional view again, we're thinking about the difference in electric potential from here to here. And notice we're moving that way. So we're starting at R1 and we're going to R2, and we go ahead and take the electric field dot product dr. And dr refers to the vector going in the direction that we're going. And since that's where the electric field is also going, this dot product is going to essentially, we won't need a dot product, we can just multiply. And since we're taking the absolute value, the negative sign that would normally be in front of this integral drops away. Okay, now we get points for plugging in. What is E? Well, E is, of course, what we just solved for. The density times R1 over epsilon naught R. Now notice that the density is a constant, R1 constant, epsilon naught constant. So pull all that out, and what's left is just your 1 over R, right? That used to be right here, dr. So now the physics in this part of the problem is over. It just becomes calculus. So we have this constant. What's the antiderivative of 1 over R? Can't use the power rule. It's a special occasion. We have ln of R, and we're going from R1 to R2. So we have the surface density times R1 over epsilon naught of, it would be ln of R2 minus ln of R1. And if we want to get a little bit fancy, then when we're subtracting logs, that's the same thing as having one log and dividing. So there we can see our answer. And over here you can see the official walkthrough if you want to take a look for what you'd get points for. All right, there's one part of this question left, which is to graph the electric field as a function of R from 0 to R1 to R2. Well, you should say to yourself when you hear that question, well, I already know what the electric field is from R1 to R2. I solved for it. It's a bunch of constants. I'll summarize those as K times 1 over R. If you plug in, so this is the same structure as y equals some constant K times 1 over x. So plug in y equals 1 over x into your calculator, and you're going to get a curve that's going down and concave up. And so we know that this is just some variation of that. We can't tell exactly what it is, but we can say for sure it's a curve that's concave up like this. Okay? So we're just graphing what we already solved for there. Next, when the radius is less than R1, let's go back to our initial picture over here. So we're in this zone. This is not a cylinder. I made that mistake. This is a cylindrical shell. So all the charge is located right there on the edge. So when I'm inside here, how much charge would a Gaussian cylinder enclose? Well, the answer is it would enclose nothing. It would enclose none of either of these shells. And if the Q enclosed equals 0, then guess what? The flux equals 0. And if the flux equals 0, then guess what? The electric field equals 0. So when we're not enclosing anything at all, the electric field has to be 0. So we can see our graph down there. Now, on the other hand, what if our R is so big that we're enclosing both of these cylindrical shells? Well, here we have a certain amount of negative charge, and here we have a certain amount of positive charge. And if we're enclosing both of those things, since the absolute values of the total charges on the shells are equal, it says, key, going back to the original facts, then I'm enclosing the same amount of charge. And if I'm enclosing the same amount of charge, my charge enclosed is 0, meaning my flux, according to Gauss's law, is 0, which means my electric field is 0. So we're back to 0 over here. All right, so that was a walkthrough of the first part of our question, and we'll be back with more. If you guys have any questions, please reach out to me or leave a comment in the YouTube video, and you can find more of me at addisonacademy.com. Thank you so much for your time.